Hi all, today we are going to discuss about scattering parameters and how to analyze the scattering parameters, which measurement method we will use for measuring the scattering parameters. This topic and all we will discuss. So, a microwave network or microwave hybrid circuit consists of several microwave devices such as sources, attenuators, filters, amplifiers, like that. So, coupled together by transmission lines for the transmission of microwave signal. The point of interconnection of two or more devices is known as a junction. So, the measurement of Z, Y, H and ABCD parameter is difficult at microwave frequencies due to some reasons. That reasons are listed here. The first one is non-availability of voltage and current measuring equipments. And second one is short circuit not easily achieved for wide range of frequencies. And the final one is presence of active devices make the circuit unstable. So microwave circuits are analyzed using scattering parameters or S matrix. So the S matrix relates the amplitude of reflected waves with incident waves. And it's also known as S parameters. Scattering parameter is also known as S parameters, are the most common network parameters used to describe the performance of the microwave devices, circuits and networks in the frequency domain. They are also the measurement quantities in frequency sweep measurements. So the most widely used microwave test instrument is the vector network analyzer, which measures accurately and efficiently the S parameters of N port networks. So the most common vector network analyzers have two ports, N equal to 2, but vector network analyzers with 3, 4, 8 and even 24 ports are commonly commercially available. So the moreover, radio frequency RF switches are available that can increase the number of ports that a vector network analyzer can handle. So what is scattering matrix in microwave engineering? It is a square matrix which gives all the combination of power relationship between input and output ports of a microwave junction. The elements of S matrix are known as scattering parameters or scattering coefficients. So in the picture shows the two port network. Here port 1 is the input side and port 2 is the output side. A1 and B1 is the input parameters and A2 and B2 is the output parameters. So, scattering matrix in microwave engineering discussed with two-port network. So, B1, B2 equal to S11, S12 and S21, S22 and A1, A2. Here the A1 is the amplitude of incident wave at port 1 and A2 is the amplitude of incident wave at port 2. B1 is the amplitude of reflected wave at port 1 and B2 is the amplitude of reflected wave at port 2. The incident and reflected waves can be related using S matrix as B is equal to S into A. So here B1 value is equal to S11 into A1 plus S12 into A2 and B2 value is equal to S21 into A1 plus S22 into A2, which is which we will get by this square matrix. So S11 is the reflection coefficient at port 1 when A2 equal to 0. So S11 value is B1 divided by A1 where A2 equal to 0. Similarly, if A1 value is 0 means S22 value is B2 by A2. Like that way, if A1 value is 0, S12 value is B1 by A2. And if S21 is the attenuation of wave traveling from port 1 to port 2, when A2 equal to 0, that time S21 equal to B2 by A1 where A2 equal to 0. So in a microwave network, if the incident power is Pi, reflected power is PR, output power is Pa, then the losses defined are insertion loss equal to 10 log of Pi divided by P naught, input power divided by output power, and the transmission loss or attenuation which is equal to 10 into log of Pi minus PR divided by P naught, and the reflection loss is equal to 10 log of Pi by Pi minus PR, and return loss is equal to 10 into log of Pi divided by PR. So what is the properties of S matrix? So S matrix is a square matrix of order n into n. So under perfect matching condition, the diagonal elements of S matrix are 0. S matrix is always symmetric, Sij equal to Sji, and S matrix is an unitary matrix, which means S into S star equal to I. This I is the identity matrix. So the sum of the product of each term of any row or column multiplied by complex conjugate of corresponding term of another row or column is 0, which means summation of I equal to 1 to n Si in Sij and Sik star, which that value is equal to 0. And also in a two-port network, if the reference plane are shifted from 1 to 2 to 1 dash or 2 dash, the new S matrix is given by like that. So in the S dash value is S dash and S value is displayed here. This property is known as phase shift property. Since S matrix is symmetric, S into transpose equal to S. So, and S parameters. So at high RF and microwave frequencies, direct measurement of Y, Z and H parameter is difficult due to unavailability of equipment to measure RF and microwave total current and voltage, and difficulty of obtaining perfect opens and shorts, and active devices may be unstable under open and short conditions. So for a two-port device, there are 4 S parameters: S11, S21, S12 and S22. S11 and S22 are simply the forward and reverse reflection coefficients with the opposite port terminated in Z0. Usually that Z0 is the load impedance, that value is 50 ohms. And S21 and S12 are simply the forward and reverse gains, assuming Z0 source and load, again usually 50 ohms. So the S parameters are B1 equal to S11 into A1 plus S12 into A2, and B2 is equal to S21 into A1 plus S22 into A2, which is framing by using this array matrix. So what is the deal with the A's and B's? A1 and A2 are the incident waves. Here B1 and B2 are the reflected waves for this two-port network, and one input port and output port is available. So, in the incident and reflected waves, in the simplified case, like Z1 is equal to Zs and Z2 equal to Zl, and which is all are equal to Z0. So, the A1, A2 and B1, B2 value is represented like this. And S parameter determination. So S11, S21, S12 and S22 is the S parameters, which is calculated in the manner of S11 is calculated by input reflection coefficient divided by, for case of ZL equal to Z0, and S21 is forward transmission insertion gain by, for case of ZL equal to Z0, and S12 value is equal to reverse transmission insertion gain of, for case of set S equal to Z0, and S22 value is equal to output reflection coefficient out, for case of set S equal to Z0. So this is the graphical view of the S parameters. So in the center we place the device under test. So first S11 input reflection coefficient and return loss and VSWR, and the S12 is the reverse gain insertion loss or transmission phase, and S21 is the forward gain insertion loss or transmission phase, and S22 is the output reflection coefficient, return loss and VSWR. So S parameters in decibels. If we are telling the S parameters in decibels, which means S11 is equal to 20 log of base 10 modulus of S11. So it is corresponds to the algebraic negative of the input return loss of a two-port with an R0 termination on the opposite port. And S12 value is equal to 20 log of base 10 modulus of S12. This is a reverse isolation or algebraic negative of the insertion loss for a passive device with R0 at ports at 1 and 2. And S21 value is equal to 20 log of base 10 modulus of S21. So the power gain or algebraic negative of the insertion loss for a passive device under matched R0 at port 1 and 2. And finally S22 is the 20 log of base 10 modulus of S22 corresponds to the algebraic negative of the output return loss of a two-port with an R0 termination on the opposite port. So Actually, a network analyzer is an instrument that measures the network parameters of an electrical networks. So the network parameters are S11, S21, S12 and S22, which are measured by using the network analyzer. Today network analyzers are commonly measure S parameters because reflection and transmission of electrical networks are easy to measure at high frequencies. But there are other network parameters such as Y parameters, Z parameters and H parameters. Network analyzers are often used to characterize two-port networks such as amplifiers, filters, but you can use on networks with an arbitrary number of ports. So the X parameters measurements with network analyzers. These instruments have found wide, almost universal application since the mid to late 1970s. So vector and network analyzer is magnitude and phases of the S parameters are measured. From the scalar network analyzer, we will measure the magnitudes of the S parameters. So most network analyzers measured 2-port parameters, some measure 4 and 6 ports. So this is the vector network analyzer, usually used to measure S parameters, and port 1 is the device under port 1 and port 2 is connected with device under test. So if there are more than 2 ports, we measure different pairs of ports separately with a 2-port vector network analyzer. So input port and output port and measuring plane 1 and measuring plane 2 which are connected with the device under test via test cables, and A1 B1 and A2 B2 is connected accordingly. So a vector network analyzer is the test system that enables the RF performance of radio frequency and microwave devices to be characterized in terms of network scattering parameters or S parameters. The diagram in the before slide shows the essential parts of a typical 2-port vector network analyzer. The 2 ports of the device under test are denoted port 1 P1 and port 2 P2. The test port connectors provided on the vector network analyzer itself are precision types, which will normally have to be extended and connected to P1 and P2 using precision cables 1 and 2 and PC1 and PC2 respectively, and suitable connector adapters A1 and A2 respectively. So the test frequency is generated by a variable frequency CW source, and its power level is set using a variable attenuator. So the position of switch SW1 sets the direction that the test signal passes through the device under test. Initially consider that SW1 is at position 1 so that the test signal is incident on the device under test at P1, which is appropriate for measuring S11 and S21. The test signal is fed by SW1 to the common port of splitter 1 and 1 arm the reference channel feeding a reference receiver for P1 receiver. So on the other connecting to P1 via the directional coupler DC1, PC1 and EA1. The third port of DC1 couples of the power reflected from P1 via A1 and PC1, then feeding it to the test receiver 1. Similarly, signals leaving P2 pass via A2, PC2 and TC2 to receiver test 2 and receiver reference 1 and receiver test 1 and receiver reference 2 and receiver test 2 are known as coherent receivers, as they share the same reference oscillator and they are capable of measuring the test signal's amplitudes and phase at the test frequency. So all of the complex receiver output signals are fed to the processor, which does not mathematically processing and displays the chosen parameters and format on the phase and amplitude display. The instantaneous value of phase includes both the temporal and spatial parts, but the former is removed by virtue of using 2 test channels, one as a reference and the other for measurement. When SW1 is set to position 2, the test signals are applied to P2. The reference is measured by receiver reference 2. Reflections from P2 are coupled off by DC2 and measured by receiver test 2. And signals leaving P1 are coupled off by TC1 and measured by receiver test 1. This position is appropriate for measuring S22 and S12. So the S11, S12 and S21 and S22 scattering parameters in the 2-port network is measured by using this vector network analyzer. and it was calculated by using these formulas.